So we're going to talk about system and surroundings. And we have defined this, if you remember,
You've seen it, right?
way back when we were talking about temperature and change of state. Okay. Start recording? Yes, it is. Okay, good. So, when we're talking about, oh my Lord, hold on. I don't know what's going on here. Okay, here we go, finally. So when we define a system can be as small as just a beaker. That can be defined as your system, or the entire earth can be defined as your system. So the system you define is whatever system you're working with, right? So yesterday, when you guys made that messy, what was it called? Oobleck, right? So what was your system? What was your system? That container, right? The container with the cornstarch and the water, that was your system. What is the surrounding then? Basically everything around it. Since your container was open, what was happening between system and surrounding?
It was mixing.
There was exchange of both material. That's why you had cornstarch all over the place, right? And also there's exchange of energy. What that means is things might be heating up or cooling down depending on which way heat is transferring, okay? Was there any kind of change in temperature? Was it getting colder or warmer as you were doing that, or no?
Warmer-ish.
Warmer-ish. Maybe, yeah, maybe a little bit exothermic, right? Okay. So, surrounding and system, again, however you define it, that's what you get to, okay? Now, let's talk about how heat flows, right? So heat transfer occurs between two objects that are at different temperatures. Eventually, the two objects will reach equilibrium. And again, we have defined equilibrium many times. We'll redefine it again. Equilibrium is defined as a point in the reaction where the rate at which the forward reaction is happening is equal to the rate at which the reverse reaction is happening. Okay, that's all equilibrium is. Equilibrium does not mean equal amounts of things. Equilibrium means the rate at which, so something is moving forward and something is moving back. So remember, melting and freezing at 0 degrees is equilibrium, which means at that same temperature that it's freezing, it's also melting. Does that make sense?
Mm-hmm.
Okay, good. So which way does heat flow? Which way does it flow? From what to what?
From
I don't know.
yeah.
High to low, hot to cold, right? So, like my hot tea, right? My hands are cold, so it actually warms up my hands. Eventually, it gets to equilibrium. Not in the case of okay. So let's look at thermal equilibrium. Heat transfer always occurs with heat flowing from hot to cold. We know this, right? So if you hold an ice cube, it melts. It melts because the ice cube at 0 degrees Celsius, your body temperature, I don't know. Well, your hands are a little colder than the internal body temperature, but it's in the 30s, right? So it's going to melt. And if you're holding a hot object, right, like a hot cup of tea or hot chocolate or something like that, then the heat transfers to your hands because this is going to be hotter. So if you have boiling water, right, a cup of tea with boiling water, obviously that's at usually less than 100 because it'll transfer the heat right away the minute you put it into the cup. So transfer of heat will continue until they're the same temperature. And the quantity of heat that's going to be lost by the hotter object is going to equal what the cooler object gains. So that's what the equilibrium part is. What one loses, the other one gains. Remember law of conservation of energy? Right? So it has to equal each other. Okay, questions on that? Make sense? We're going to get to the math in a little bit.
Today?
Mm-hmm. Mm-hmm. Are we good?
Mhm.
Yes. All right, so quantity of heat lost by the hotter object and the quantity of gained by the cooler object is going to be equal to each other. Again, that's where law of conservation of energy comes in. Now, we've talked about exo and endothermic processes. Can anyone tell me what they were?
Exothermic is one that like pushes out, and endothermic is one that takes in heat.
So exothermic heat is released. Exo, think about exit. Endo, taking in, right? Heat is taken up. So we've talked about this in terms of condensation, vaporization, and all that good stuff. So exothermic heat is lost from the system. So what that means is that temperature in the system decreases because heat is going out. Endothermic is going to be exact opposite. Heat is transferred from the surrounding to the system. So this one goes system to surrounding. This is surrounding to system. And so temperature increases in the system. Because heat is being taken up, that means it's going to get colder. Okay, so endo taking in, exo releasing. And then we mentioned delta H tiny bit when we were talking about change of state. Delta H is the same as heat that we're going to look at right now. Remember how we calculated the delta H mass times that amount of the energy that was given to you? All you had to do was multiply. Remember that equation?
Mm-hmm.
Okay. So we're going to do something similar, but we have to look at temperature change because what you calculated were just change of state. And in a change of state, there is no temperature change. However, in other parts of this, system and surrounding and the reactions that are happening, there's going to be a temperature change. And that's the reaction with the burning of food to find the calories, right? There's a temperature change, and that's how you calculate how many calories the food has. Okay? So far, so good? So when we look at enthalpy is just heat. For our purposes right now, enthalpy and heat are going to be interchangeable. And if we were talking about exothermic reaction, so this is the system before the reaction and then system after the reaction. So delta H is going to be less than 0. Less than 0, a negative sign on an energy means that energy is released. Negative sign does not mean a negative number. In other words, negative 100 kilojoules is greater than negative 50 kilojoules. Because the negative just is an indication that there is energy being released. That's the only thing that's happening there. So if I have an exothermic reaction, I know it's exothermic because the delta H value has to be negative. Okay, again, a negative value just means energy is released. If I have the opposite, then obviously the opposite is true because the system after the reaction is higher than the system before the reaction. So it's taking up heat, right, surrounding to the system. Then delta H becomes positive. So positive delta H means energy is taken in. That's an endothermic reaction. Negative delta H, bless you, means that energy is being released. It's an exothermic reaction. Reaction. RXN is the abbreviation to reaction. Okay, so delta H of the reaction greater than 0, endothermic. When the delta H of the reaction is less than 0, then it becomes exothermic. Now we'll do some math and look at the units. So we're going to use both calories and joules to calculate things. And we need to know the conversion factor. So let's look at this. Joules, which we don't see on our food packages, right, because we live in the US, but we do see calories. And 1 calorie is equal to 4.184 joule. 1 kilojoule is 1,000 joules. And what is a calorie defined as? A calorie is defined as amount of energy that is required by 1 gram of water to increase its temperature by 1 degree Celsius. So how much energy it takes to increase the temperature of 1 gram of water by 1 degree. And that's 4.184 joules, which is equal to 1 calorie. A kilocalorie, which is just a capital C really, is the one that we use on our nutrition facts. Yeah.
So in Europe, they use joules instead of calories?
Kilojoules, yeah. Mm-hmm.
That's crazy. It's like, oh, I'm
lot
trying
of
to
the
lose those
yeah.
joules. How many joules do you have?
Kilojoules. It says kilojoules. And it'll say energy.
Oh, they'll say kilojoules.
Mm-hmm. Yeah, if you've ever even imported things, like you look at the packaging, it'll say kilojoules.
That's insane. I never thought about that.
But you guys, it's not something you pay attention to because you're used to just calories,
I've
right?
also never been to Europe, so like I wouldn't know. I feel like you're just insulting the entire American population this much.
By saying that we use calories and not joules.
By saying that like we didn't know that like.
I think that's just you, Evan.
You knew they use joules in Europe. Kilojoules.
It's like they say kilometers.
They use everything different.
They just
Besides
different-
America.
I thought joules was like a scientific term only.
There's
And
joules
it's like,
like
yeah,
it's
it's like
like
how they use
Evan, it's like how we use like kilometer or like
centimeters and
Yeah.
stuff.
Miles
And we
and
use that in
kilometers,
science,
inches
too.
versus
Well, I
centimeter,
understand that
right?
now, but I didn't know that
My
before.
mom still thinks in like kilometers.
yeah, same with my
Where's your
mom.
mom from?
She's from Russia.
My mom
in
thinks like
Canada.
that because when she was like younger, they were going.
That's all you, yeah. And plus, that's all you're taught. We're
Guys,
not-
America should
you're-
really change it. It's
Any
so
other
stupid.
country
I mean,
is
they
not
try to
taught
do
in
it.
miles, right? But you don't have a choice on a daily basis. You do you see miles and inches and feet. But when you come to science class, then you have to convert everything to international system of units, which is not the case in other countries because when they look at the science, there's no miles and yeah, the entire world
Guys,
uses
America's
Celsius
really
and stuff
It's
like that.
pretty much just the U.S.
Yep.
Although they tried to change like the 70s, but it didn't work.
It didn't work. It's a costly change.
So like
All
now
right.
my mom doesn't understand like the units that we use
That's a good thing.
Why?
because they tried to change it when she was younger.
And so when she was in school, she learned in the units.
Mm-hmm.
All right. So, what I told you, remember about calories? A capital C is a kilocalorie because that's 1,000 calories. And again, we don't want to write on a bag of chips that's 180 calories, 180,000, right? Nobody wants to even see that. And I think it's a,
Then they're gonna think you're gonna die.
yeah.
Nobody's gonna want to eat your food.
Yep. Exactly. Okay. All right. So let's do some conversions of what we're looking at.
Ooh.
So let's say units of energy. If I have 3,800 calories, how many kilocalories
3.8.
is that?
3.8.
And how many joules is that? So you have to think of the conversion here.
Wait,
So let's
I'm
look
gonna
at this
need-
conversion.
I'm gonna need some.
1
like-
calorie is 1,000 small calories,
Wait, I'm gonna need my calculator for this.
right? And then this is another conversion. This conversion factor I'll give you. I don't expect you to memorize that a calorie lowercase is 4.184 joules.
My calculator had a battery, so I cannot answer that question.
You can do that on your own time.
In my head.
All right. So now let's talk about how we find the actual Q. By the way, Q and delta H are interchangeable. But
Why?
we're going to use Q for this formula, and I'll show you what the formula is. So we already said endothermic heat is added, right? Temperature increases, that's plus Q. Exothermic heat is lost, and we have a negative Q, right? Negative H, negative Q, same thing. Heat capacity is the amount of energy that a substance requires in order to increase its temperature. So if you think about substances that have high or low heat capacities, what does it mean for a substance to have a high heat capacity versus a low heat
It can
capacity?
hold more heat.
So does a high heat capacity heat up faster or slower?
Faster. Slower.
Slower, right? So you have to think of, if I'm talking about water has high heat capacity, but if I'm talking about, let's say, aluminum metal, that has low heat capacity.